to the general purpose functional programming languages like Scala and Haskell. It's specifically aimed at doing tensor computations very efficiently and potentially also allowing auto-diff through your code. And so, well, that was developed by people at Google Brain. And I think they did the best jobs that they could at producing such a thing embedded in Python. Fortunately, there are just massive limitations to doing this inside a dynamically typed interpreted language like Python. And so, you know, you can do pretty much everything with it, but it's not a very nice language to develop non-trivial codes in. It's horrible to debug, and there's no real way of fixing it while using a language that's embedded in Python. So the Google Brain people are developing this language called DEX, and in fact, several of the people who were involved in the development of JAX are also involved in the development of DEX. So you'll see lots of similarities between JAX and DEX. You'll also see a lot of similarities between DEX and Haskell, and increasingly Scala. Okay, so again, the people who developed JAX, several of them were Haskell programmers and were inspired by the functional programming ideas of Haskell when they were developing JAX, and they're using the same ideas in the development of DEX. So DEX started out very reminiscent of Haskell, not identical, but with a very reminiscent syntax. It's actually written in Haskell. But the idea is that it's a pure functional differentiable array processing language, but it is a standalone language. So it's not embedded in Haskell, it's not embedded in Scala, it's not embedded in Python. It's its own standalone language, so it's got its own syntax. It's got a REPL, you know, you can use it in a similar way to use Haskell. So that is the idea behind it, and the idea is that you're starting again with a language, so there's no reason why we can't design the language properly, make it a nice, strongly typed, pure functional programming language, but with particularly good support for tensors, and make the whole language differentiable as well. So that's the idea behind it. It's very cool. It's still quite experimental. It changes quite regularly. So every now and again, they will update the syntax and your code will break, right? So you should be aware that it's not like stable as something like JAX, but it's super interesting. And I think whether or not this turns out to be the next big thing in scalable statistical computing, I think there are a lot of good ideas in it. And I think, you know, whatever the next big thing is, it will probably be, you know, similar to this in some way. Okay, so I think there are a lot of good ideas here that we'll learn. Like I say, the people who are developing it are Haskell people. It started off looking very like Haskell. As we'll see as we go along, it's starting to look a little bit more like Scala. You know, I think they decided that actually some of the decisions Scala have made around syntax actually make them more readable, natural code. But you'll see lots of similarities with both. Okay, so you should recognize lots of things. And I'm aware that not everybody's got DEX installed. That's fine. So I'll try not to, you know, rely on that too much. We'll just work through it. And incidentally, like a lot of these languages, have you know, some sort of facility for literate programming. So you know that in R or Python you can write our markdown or whatever something and embed code blocks in it. You can do the same with Scala. DEX actually does it the other way around, which is interesting. So instead of having a markdown document that you embed code blocks in, you have a DEX file that you can embed markdown blocks in. Right? So it's very similar, but sort of slightly different, and so that's kind of key. But the same idea. So we can have these kind of executable sheets where the code is run when you compile a markdown document, and you can see what's going on. So that's nice. Okay, so you just say x equals 5 when you want to declare a immutable value. Just like Scala and Haskell, you can ask for the type of something at the REPL by doing :t. So that will tell you that this is a natural number. So the type system in DEX is quite sophisticated in lots of ways, and in some ways it's more sophisticated than Haskell or Scala in that it has a proper type system for indices. Okay, so if you think about tensors, arrays, vectors, etc., you index into those arrays, and its type system is, as we'll see, its type system is built in such a way that you can deal with tensors very safely. And so in particular, you can have named indices, and you can make sure that all of your tensor operations are safe. So for example, you can't multiply two matrices together if they're not conformable. And that is a compiler time error, right? So it's not a runtime failure. With a compile time error, if you try to multiply matrices that are not conformable, you have proper typed indices, right? So you can't mix up your tensor indices, right? When you bug in the tensor programs, right, you get the wrong index at some point. You can't make those errors easily in the index because everything is typed, the indices are all typed, and everything can be checked at compile time to make sure that everything is conformed. It's like a really powerful thing that certainly you can't do trivial in Scala, and even in Haskell, that's not a trivial thing without various language extensions. Okay, so it's immutable, it's got immutable collections. So again, a little bit reminiscent of Haskell, you just use square brackets to denote an array, which index is known as a table, but it's not like a linked list in Haskell. So in Haskell, this would represent the linked list. This is not a linked list. This is an immutable array. So very much like the vector type in Scala or the immutable array or a JAX array. Okay, so an immutable array. And so you can like map it or whatever, but actually looking at the type is quite interesting and informative. So this is a fin5 to a float 32. So what does that mean? Well, if you think about it, an array like that is essentially like a function that maps an index to a value. Yeah, and so that's encoded in the type there. Yeah, so if you've got an array of floats, that's really like a function that maps an index to a float. Okay, and the index here is fin5. Okay, so the index isn't a natural number or an integer or anything like that. The index is a fin5. So that really means the numbers from 0 through to 4. Yeah, and they're indices. And the number 2, okay, as we'll see in a second, is not the natural number 2. It is the index 2 of type fin5, and that would be different to the index 2 of type fin10 or anything else, right? So the type system is really capturing the indices of the array and what indices are allowed and what conforms and matches, right, in a really strong way in the language at the type level. Okay, so this is like a very cool thing. Okay, so if you want to index into that array, in principle, we can't just say, give me the element at position 2. Okay, because that isn't an index. 2 isn't an index. 2 might be a natural number, it might be an integer, but by default, it's not an index. So in principle, we should say the index 2 of type fin5, right? Because that's the index 2 of the type fin5. Yeah, and so that's what we should say if we want the element at position 2. However, like all of these languages, it has type inference, and so in fact, if it's not ambiguous, you can just let it infer the type. Okay, so 2, actually, if you're indexing into B, the 2 must be of type fin5, and so the type inference system will infer that for you, so that's okay. Okay, what about actually updating an element of the table? Well, actually, the way you write code in Dex, this isn't something you would normally do. Okay, so you would actually use this for construct. For doing stuff like that. So it isn't something you would normally do, but you can do it. And so it's going to look a bit mysterious at this point. So these for things are not regular for loops. They're more like for comprehensions in Python, say, for expressions in Scala, etc. So we'll come back to this for construct in a second. But essentially, you just say, well, if my index is 2, then I'm going to return the value 9, otherwise I'm going to return whatever the value wants, and that's going to give you a new array with the element updated. Okay, but all of the usual things we've already said apply. That doesn't necessarily imply that we copy the element array, etc. Okay, so very much like a JAX array. That's what I'm going to go-to way of thinking. Yeah.
it keeps giving me an error that the script of learning listed on a
Yeah, so if you put it into a file and source it, I think it will work. So it was actually an issue with some Haskell code as well, that when you just type in stuff one line at a time in the REPL, you can't always infer anything and you have to put type ins on. And so it'll be the same here. You'll need to type in to get it to work if you're typing it one line at a time in the REPL.
Okay, I guess because you're telling it big one thing,
Which you haven't done exactly, it hasn't got it yet. And there's probably a paste mode, so in Scala, there's a paste mode to do this. I can't remember if there is in the dev REPL or not. Okay, so that's, yeah, we're going to come back to that. But what can you do? Well, you can map and reduce, just as we've seen before. So this is how you define lambdas in DEX, just with a slash notation, very similar to Haskell. So that means, so if you look at the thing in the round brackets at the top there, that just means the lambda with the indeterminate x that returns the value 2 times x. And so we're going to map that lambda over the collection B. That does the obvious thing. For matrix vector multiplication, DEX has this nice notation where the dot basically points to the thing in the lower dimension. Okay, so if you've got a constant on one side and the vector on the other side, you'd use dot star. If it was the other way around, you'd use star dot. You could also do the same, we'll see later, with matrix vector products, where if it's a matrix times a vector, the matrix has higher dimensions, so you put the dot on the right, etc. So we'll see examples of this as we go along. But it's just, again, just trying to make the syntax as unambiguous as possible, which is probably a good thing. It's a little bit ambivalent about whether it likes Scala notation or Haskell notation, and again, that's because it started out more like Haskell notation and is evolving more like Scala notation. So whether you write some space V or some brackets V, it's kind of up to you. In fact, it's the sum brackets V is really the canonical DEX these days. Reduce, as we've seen before, again, it likes you to provide the 0 to reduce. So again, we're very much dealing with one-eyes here. Again, it's assumed it's monoidal, and so it can be reduced, tree reduced in parallel. Folds are very much like reduce, but a fold, I probably haven't explained, the type of the result can be different to the type of the elements, right? So if you're doing a reduce, you know, if the elements of the vector you're reducing are, say, ints, then the result of the reduce must be ints. With a fold, you can transform the value to another type as you fold, yeah? So the result doesn't have to be of the same type as the elements of the thing you will put together. But, again, similar sort of notation. Yeah, but DEX really goes big on 4 comprehensions, which I don't know whether I like it or not, but it's because in some of these tensor computations, it's just much more convenient to express them in indices than just, you know, doing vector matrix operations, right? Sometimes it is just handy to be able to refer to the information. So DEX has produced this nice 4 comprehension that allows you to use indices as if it was like a for loop, but actually it isn't. Okay, so really, when you do this for I is just an indeterminate, meaning the current value. It's not really a counter that you're counting through one value. It's not really how it's working, but it gives you a syntax that looks like that's how it's working. So here, all we're doing is mapping, right? We're just taking each element and multiplying it by 2, but we're writing it in a way that it sort of looks a bit like a for loop. Okay, and this can be powerful for kind of high order tensors doing clever things. Yeah, we can. So the whole type inference thing. So if we say for I over fin 8, well, that means that I has to range over the indices from 0 to 7. And so if you're always returning a 2, then it has to return something of length 8, all containing 2s. If you want different elements, again, this again explains a bit about DEX types. Okay, so if we're letting I range over the indices in fin 6, then I is going to be an index. It's not going to be a number. So the function ordinal we'll turn an index into a natural number. So first of all, we turn the index into a natural number, and then if we want a float, we then have to turn the natural number into a float with a function n to n, yeah? So these type conversions are not automatic, right? You can't just treat an index as a number. An index isn't a number, but if you apply the functional ordinal to it, it will give you the number corresponding to that index, yeah? So it's very fiddly with types, but it prevents a huge class of errors. And you see that as soon as you go to higher order tensors, right? We can call height bin 3, width bin 4, and now wherever we refer to that index, we refer to it by name as height and width. You can never mess up where you use a height where you should use the width, right? You will detect that at compile time if you do, not at runtime, yeah? So it detects at compile time a whole class of errors that you don't want to happen, but do happen all the time. Yeah, so it's actually it's a really clever use of sort of dependent typing. It's not a fully dependent type system, but it's got elements of dependent typing that that are perfect for this kind of tensor array type computation. Yeah, and so again here the type of two-dimensional array is bin 3 to bin 4 to float 32. Yeah. You supply 2 indices and you'll get back a float. If you provide 1 index, you will get back a function that maps an index to a float, i.e. you will get back a row. Yeah, so that is the type of an array. Again, it's kind of nice that it invokes this notion of an array being a function that maps an index to a value.
Sorry, the last set, this sum of
What am I looking at?
sorry, in where you've got 0, 1, 2, 3, 1, 2, 3, 4.
Yeah. So if you look at the way I've defined it in the for comprehension, I is your height index, j is your width index. Yeah, we're going to convert I to a number, j to a number, then we're going to add them, then we're going to convert to a float.
Why do you be 2? In the previous example.
As if you have the first element of with vectors.
Yeah. That don't make sense.
Because the top element is 0, 0. So you add a 0 and a 0, you get 0. The next element, whether you go along or down, is going to be 0, 1 or 1, 0. So that's going to give you 1. And what we've got are the rows of the table.
Okay.
Does that make sense? Okay. But interestingly, right, if you put a minus sign in there, it would have crashed. Why would it have crashed? Yeah, because you can't always subtract natural numbers. Yeah. So if you want to subtract natural numbers, you've got to be careful. Like you first of all got to convert them to integers and then subtract it. Yeah. So it's fussy, right? About if it's a natural number, you can't necessarily subtract them.
Darren, is it possible to find the type instructors for the indices to specific dimensions? So if you had named dimensions,
Yeah.
like for climate depth,
Yeah.
then is it possible to find an index type to that particular dimension? So you would.
Well, it depends what you mean. So it's not necessarily enforced, but if you get it wrong, it will give you an error at compilers, right?
So I'm just thinking you could have, so if you have 3 by 3 matrix then
Yes.
type would have the same base type.
Yes.
And then they would be interchangeable. So you're not still the type of types and the type signature. We're just seeing a base type.
You are, you're right, yeah. So good question. But I don't think you can actually, because you can like recreate texts with the indices with the different, because there aren't actually multiplications where you want to do that. So I don't know if there's any way to enforce that, but yeah, that is an interesting question. But I guess that's a good reason, yeah, to keep dimension difficulties slightly deeper.
We construct them, you know, that, and then convert that to what it impacts.
Sorry, say that again?
You could do something like maybe create an num type and then use that, then cast your inputs to dimensions.
Yeah,
If you're saying like on the table, you might have to then you can like named columns essentially. Make sure we index them to the right. Right type of column.
yeah. So, yeah, I feel like this is something that that they have discussed. So maybe if you go through the next tutorial, they will have an example of this. It sort of rings a bell that there is a way to do this, but I now can't remember exactly what it is. But yeah, it is a good question that if you've got an n by n array, there is still a potential for messing up your indices. Okay, so if you look at function definition, you'll see that it's sort of more Scala-like than Haskell-like these days. It didn't start out that way, but these days it is. So you def log fact, n is a nat, and the result is a float. Okay, so we don't need to worry about somebody passing in a negative number. They're not going to, they won't be able to. And we can just use our for I notation for that if we want. Just do it the usual kind of heap way, and that all works fine. Just like Jax, because the language is differentiable, there are issues with just allowing completely general recursion. So they have to do something to make up for the fact that they don't allow general recursion. Again, Dex has taken quite an original approach to this. So they have what is called an algebraic effects system. And so they basically have a mechanism that allows you to manipulate something that looks like a mutable state, but in a safe, pure functional way. So again, if you know about functional programming, you'll know about things like the state monad, which kind of does the same sort of thing. Everything's pure functional, but it's almost like you're mutating a state within your code, but you're not really. There are other things going on behind the scenes. And so this is the same with the state structure here, that this yield state basically allows you to create something that looks like a variable called state there. So this slash state dot means create something that behaves exactly like a state called state. I can retrieve the state with a get command, and I can reset the state using colon equals, right? So it looks like I'm retrieving state and I'm mutating it by resetting the state. Now, again, this is kind of a trick. It's all pure functional underneath, but it gives you a construct that looks like you have a state that you can mutate. And if you have something that looks like a state that you can mutate, then there's no reason why you can't have a flash. Yeah. So it's kind of clever what's going on under the hood here, but it's a structure that you can deal with, and you can use to write, loops that where you don't know how many iterations statically, for example. In a perfectly sensible way, and that's what we use for the logistic regression example. So so Dex does a number of quite clever things. So in a way, it's a little bit like Jack's just giving you a while loop construct, but actually it's a lot more flexible and powerful than that. What it's actually giving you is something that sort of behaves like a mutable state that you can then use to construct while loops if you want to.
I think there is something that a little bit unsatisfying about this, because the point of functional programming language is that it's fast to use things differently. Yes, and it's really construct you basically come back to your old way of thinking.
So I know what you mean, except that this really isn't a mutable state. Right? So it sort of behaves like it, but it only in a very limited context can you do this. And I actually don't even know if you can auto do do that. Some language is supposed to be differentiable, so I'm guessing that you can. Yeah, so it's something that looks a little bit like a state, but it's not like you're really going to confuse this for a real kind of useful variable, right? So it's a very limited thing, very limited scope. You're very controlled on what you can do with it. So I know what you mean, and it feels like a bit weird to me as well. But having used the state monad in the functional languages, I know that it's essentially the same as that, and it's okay. Really.
Points from that function of true and false.
Yeah, exactly. So the way this while construct works is that
You've got two nested lambdas there.
yeah. So I haven't explained this at all. So the way the while loop works is obviously you need to decide whether to continue or not. And you decide whether to continue or not, depending on whether the lambda inside there returns true or false. Yeah. But then the value returned from yield state is the final value of the state variable. Yeah.
Yes.
But interestingly, what that then does is a very naive sequential sum of 32-bit floats, and actually it's not very accurate. It's kind of terrifying, Which is not what it does when it does the reduce, because when it does the reduce, it does the tree reduction, which is much more accurate.
Things like break and continue then.
Yeah. Well, not in the normal sense, right? But there are these algebraic effects, and some of them allow you to do things like that. Okay, so not in the normal sense, but DEX does provide constructs such as the state construct that allow you to do things a little bit like that. I was thinking something a bit. Yeah. There are other examples. So this was yield state, but there are other things like this that are built in as algebraic effects inside the language that allow you to do these sorts of things. But you don't have complete freedom to do whatever you want to do. Right, and so what about currying? Well, again, it started out early versions of DEX, everything fully curried. Like Haskell, it's sort of evolved to be more Scala-like now. So you can actually say how you want your things to be grouped. And so here we group together the M and the C because we expect those to be provided together. And then we're going to get back a function that maps a float to a float. And so the lambda then has to take an X and map it to an X plus 6. So this is more Scala-like than Haskell-like now. And that works in exactly the usual way. And so the type of lin fun takes a pair of floats to a float, whereas the type of F, after you've supplied the first two arguments, just takes a float to a float. Yeah, so that probably makes sense.
Sorry, I'm looking at this kind of definition. That's not this one. It's just the same since there's any brackets that we access.
Well, it is and it isn't. So in DEX, you have to name the arguments and the argument list has to be enclosed in brackets, just like Scala and not like Haskell. So in Haskell, you just say float to float to float to float. You could put brackets around if you wanted, but it would just be the types. You wouldn't have the names of the arguments. So this looks much more like Scala. Okay. Right. So any more questions before we go on to the logistic regression example?
Yeah, sorry, you don't need to name the floats to the last.
No, because again, the way you should think of this is it is a function that takes two arguments and returns a function. Okay, so the return type you never give a name to. Yeah. But here the return type is the function float to float, okay? So it's a higher order function. So you give names to the things, to the arguments of the function. The arguments of the function are just M and C. The return type is the function float to float. So that doesn't have a name.
You could construct a name within the definition of functions.
Exactly, which is why you got the slash X in there, yeah. Okay, so have a look at the example. I do have an H100, that's good. So again, if you do have Dex installed, you should be able to run all this, it should all be fine, but I know that not everybody has. Yeah, and so, like I say, Dex is kind of interesting. You can just put little markdown blocks inside your code files, which gets them to render nicely, which is kind of cool. So it's mainly just code, but I've just shoved in a few headings and things just to tidy it up a little bit. So there's all the usual crap at the beginning, which is much like in every other language. So we won't worry about that. Let's get on to the gradient descent. So we define our log likelihood. So that takes a B, right? So in fact, it's using. So there are lots of ways you could do this. So we actually have the X and Y defined in scope when we define the LL here. So we don't need to explicitly include the X and Y in the definition of the log likelihood. We could do it differently, obviously, but here the log likelihood just takes B, which is a vector, and so the vector has type here finite float. Okay, so it's a vector of 8 floats, and it's going to return us a float. And again, the syntax looks kind of like, well, again, it's a bit of a mishmash of Haskell and Scala. But notice the star dot there, right? That's matrix vector product. So the 2 stars means the thing on the left is a matrix, and then the dot means that the thing on the right is one-dimensional, something like that. Yeah. And so if you were doing a vector matrix product, it would be dot star star. Yeah. So that's that. Element-wise product is just star, and yeah, rescaling is easy with a map, I think. It has the same issue with that Haskell has with unary minuses floating around. It's sometimes easy just to negate. Again, you could just auto diff. Okay, so the grad of the log likelihood is just the lambda that returns the grad of the log likelihood to the X. Okay, so you just auto diff the gradient, that just works. Your one-step update. So here I have got the learning rate as the first argument. So you provide the first argument, and then you get back a function that maps your old B to new B. So you define that with a lambda, then gives the argument to the second bit. So that's just B naught, it's learning rate times the grad likelihood. And then the ascend function should again be looking pretty familiar at this point. And we're going to use this state effect in order to mimic something that looks like a while loop. And that will just work as we've already described. So we're having to pass through as the state both a value and the iterations remaining, so we can terminate if we run out of iterations, even if it hasn't converged. So that's the state that gets threaded through. And in fact, the B naught x equals get state tells you what's happening there. Okay, so you're pulling the B naught and the x out of the state, and then at the end, you'll reset the state to be the new B, and the x decremented by 1. And otherwise, I think it should all be reasonably similar to the examples we've seen before. So yeah, so I really like this language, and it'd be great if everybody really bought into it. It's a much nicer, safer, elegant language than Jax, but produces potentially as fast. Right now, it doesn't, in fact, because it's not optimized as well as Jax, so it's a little bit slower than Jax, but not much. But it does the auto diff, it does the compiling to multi-core, it does the compiling to GPUs, etc. That all works, just currently not quite as optimized as JAX, but it's actually a nice programming language as well. So, like I say, whatever future languages for statistical and computing look like, I hope they look a bit like this. This has a lot to recommend it.
Okay, so any more questions about DEX?
Sorry?
Is it a lazy language like that?
No, it's straight by default, like most of the languages. Yeah, but again, like Scala, you can do lazy language, but it's straight by default. Right, okay, so that's DEX. But then it occurs to me that what we haven't talked about yet is anything stochastic. And so there's a whole separate issue of how you do stochastic things in pure functional languages. So I thought if we were finishing off talking a little bit about how you do randomness in pure functional languages. So, as probably we all know, computers are really deterministic. So when we talk about random number generators on the computer, we're generally talking about pseudo-random number generators. I mean, in fact, most computers these days do have hardware random number generators built in, but for Monte Carlo simulations, you're probably better off with a pseudo-random number generator anyway. And so you probably know that the way these things actually work is the random number generator has some internal state S, and it has some function that updates that internal state, and then it has some other function that turns that internal state into a random number, and that might be a lot of number, it might be just a 0, 1, uniform 0, 1, or whatever, right? So that's the basic structure of most random number generators. There's a function that updates the internal state, and there's a function that turns that internal state into something that you can use in your program. Incidentally, that internal state isn't the seed, yeah? So there's a separate process that takes seed and turns that into an internal state, yeah? Seed is often something quite short, like an int or a long or something like that, whereas the internal state might be very big, right? So there's some separate function that turns the seed into an internal state, but that's a different matter. But there's an internal state that gets updated each time you request a random number, and there's a way of turning that internal state into an actual random number that you can use. So obviously the state space of S has to be big, because if it's a deterministic function, it's going to repeat eventually, right? So you think of the internal state as living on a big circular lattice, and eventually it will go round and round that big circular lattice, but you really hope that the circle is big enough that you don't during the course of a simulation, but that's a good picture to have in your mind. And then there's a separate function that takes you off the circular lattice back into the realm of things that you can use in your program. Okay, that's good. So typically, the magic is embedded into the function f. Okay, so f will be some very complicated nonlinear function that's, kind of one way and not predictable and blah, blah, blah. And g will typically be a very simple function that will take that state and turn it into something you can use, like just take a block of bits and turn that block of bits into something like that. Okay, so that's traditionally how a lot of uniform random number generators worked. But it doesn't have to work like that, and a lot of generators these days don't. Okay, so in fact, the f that updates the state could be a really simple function, like add 1 to the current internal state, right? That would be then like a counter. And the function that takes you from the internal state to the thing you use could be a very complicated thing, like some, very complicated cryptographic hash function that turns that very simple internal state into a random number that you can use in a very unpredictable way, right? That would be another perfectly good way of constructing a random number generator. That would be called a counter-based generator. Yeah. So the complexity can either be in F or G. There are pros and cons. Okay, so that's when people talk about counter-based generators, that's what they mean. They mean that the complexity is in the G function, not the F
right? But that's not really what we're talking about. What we're really talking about here is how on earth does this work in a pure functional language? So in a regular programming language, mutable programming language, you might have a function called random, say, that would first call f to update the hidden state, and then call g to give you back a number. Yeah, and so that internal state would be mutated. Okay, so you'd call the function f to update the mutated state, and then you'd overwrite your current internal state with a new internal state, so that the next time the function's called, you're updating that new mutated internal state. Yeah. So in fact, conventional random number generators rely on you being able to mutate that internal state of your generator. And whether that internal state is a global variable or a local variable that you pass around the function, that all depends. But the fact is that most generators in imperative languages would rely on you mutating the internal state every time you ask for a random number. And that's obviously a bad thing. So what do we do? Well, conceptually, what you do is you carry around the internal state with you throughout your program. Okay, so what you do is, if you had a function random, say this is just like Scala notation, if you had a function random, what you do is you'd pass in an internal state, and you would get back a new internal state and the number that you want to use in your program, and it'd be down to you to unpack those, to use your random number as you see fit, and to keep track of the new internal state, so that the next time you want a random number, that's the internal state you pass in to this function. Right? So conceptually, that's how you do it. Okay. So if that sounds a little bit annoying, well, in fact, it turns out that monads come to the rescue here, and in fact, you can wrap this up in such a way that it's just like using a random number generator in imperative language, or at least it looks like you're using the imperative random number generator, because the internal state kind of gets propagated through the context of the state model. Okay, the details don't matter here, so it doesn't have to be as clunky as this in practice, but in principle, this is what you do in a functional language. You carry around your internal state. Okay, so what's the problem with that? Well, the problem with that is it's an incredibly sequential thing. Okay, so you're keeping track of this internal state that you're updating. But if you want to now do parallel computations, what do? Well, you've got a problem, right? Because you only have one internal state, right? And you only have one way of updating your internal state. So if you want to branch, right, you're just stuck, right? There's not really anything useful you can do. Okay, so traditional random number generators were very sequential, didn't work very well in a parallel context. Okay, so this is how you solve the problem of random number generation in a functional language, but it doesn't solve the parallel problem. Okay, so how do you solve the parallel problem? Well, there are lots of ways you can do it. And so traditionally, the way you do it is using something called a parallel pseudo-random number generator. And so how do you think about those? Well, I think the best way to think about those is, instead of your state living on a huge circular lattice, you have this huge circular lattice, which you advance each time you request a random number generator. But you also have a kind of, as well as being able to go around, you can also go over the top, okay, which is through a different processor. Yeah, so you actually think of your state space, instead of being as a big circular lattice, it's a big toroidal lattice, okay, where the circles around your toroidal lattice are what each processor will traverse, and the sequences around, right, the different circles correspond to the random number states that will be used on different processors. Yeah, and so the idea of these pseudo random number generators was the states are all distinct. Okay, so it wouldn't matter as long as different processors were using different runs of this toroidal lattice, different circuits on this toroidal lattice. They would never overlap and never interfere with each other. Right, so this is how these parallel pseudo random number generators work. Okay, so that was a perfectly good way of doing things back in the days when everybody was doing their parallel programming on a Linux build cluster with 8 CPUs or whatever. And so you just made sure that each CPU had started on a different circle, and then they could all just do their own thing. Everything was fine. But in the modern context of what we call CPUs, GPUs, you don't know how many threads you've got, you don't know what you're doing, you just decide to split at some random point. And, you know, actually keeping track of which processor has which rung of the ladder, right, is actually just as difficult as everything else, right? So that actually just doesn't really work. So I think that this idea of parallel pseudo-random number generators actually doesn't really work properly in the modern world. And so what people are using typically these days, and in particular the default in both JAX and DEX, is a splittable generator. Okay, so how do splittable generators work? Well, the basic idea is instead of having a function that just advances you, take in an old internal state and give you a new internal state, you actually have a split function, which takes an internal state and gives you back two new internal states. So it's an incredibly simple variation on the above, but it actually now allows you to do things in parallel, because now you have two C's, so you can give two states, so you can give one state to each of two computations, and those computations can proceed in parallel. And the trick of designing these splittable generators is you make sure that this split function not only gives you different internal states, but subsequently when you do additional splits, you get kind of a tree of states, again, that are guaranteed not to overlap. Okay, so you get this massive tree of states that don't overlap, or at least incredibly rarely overlap, and so it's safe to use the different splits in different parts of your program in parallel with each other any way you see fit, right? And this really does solve then the parallelism problem. Okay, so that's basically the idea, and then you do have to carry this around in some way or another, just like you would in principle in any functional language. Okay, so yeah, so I mean, hopefully it's kind of clear. So here in DEX notation, you have a key. Okay, so the internal states are typical keys for historical reasons. So you take a seed and you use that to produce a key. So that's your initial key, K0. Then you can split that key into two new keys, say, and then you can use those keys to do different random computations. And the point is that those different random computations can run in parallel. There's no problem with them running in parallel, because they've each got different keys that they're initialized with. And so whatever they do, you know, they might do other random things, they might split the keys and more, blah, 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 but it doesn't matter, because you started off with two independent states that can be further split to give new independent states. They're never going to interfere with each other. Everything's fine, right? So they solve the parallelism problem by splitting. Okay. So, yeah.
Can I just ask a small thing?
Yep.
Like, it doesn't matter if one expects different threads to be using different numbers.
No, precisely because basically it's just the root of a tree, right? So your internal state is the root of the tree. So whatever your stochastic function does, right, it's just going to flesh out bits of that tree, and because they're guaranteed to be independent, everything's fine. So no, they can use different numbers of random numbers, they can ignore the key, you know, it doesn't matter. Right. However, the problem is you have to carry around this key and make sure you pass it into all of your functions, just like you would generally. Okay. Now, so what the DEX people are working on, I've told you they've got this like neat algebraic effect system that they use for like looking while loops and things at state. So they are trying to come up with a way of having an algebraic effect called random that again hides a lot of the details of using split generators for you from you. And so that sounds like a very cool thing, but you know, there's nothing to look at yet. They're just thinking about it. So for now, you have the responsibility of carrying it around, making sure you split it before you use it, and don't mess up. Yeah. So the risk here, right, is that you don't split the key and you reuse a key somehow. Yeah. And if you do that, then that's going to mess up the results, and that's problematic for two reasons. So it's problematic because it messes up your results, but it's also even more problematic because it's not something that a compiler can easily check or detect, right? And it's not very easy to spot or debug, right? Because debugging Monte Carlo flows is always a bit tricky, right? So it's kind of a dangerous thing that's easy to do and not easy to spot. So there is an issue with these splittable generators. So having better mechanisms for managing these splittable keys would be good. But for now, you know, you're in charge. you split the key and make sure you don't use
Can I just ask a question?
Yeah.
Very stupid. So if you have 1,000 of parallel threads,
Yeah.
you want to split your key in 1,000.
it. Yes.
You want to do it splitting once and then splitting again.
So conceptually, you could do that. In practice, they all split many times multi-way, and so we'll see an example of this.
Okay.
So you can you just say I want to split it 1,000 times, and it will give you back an array of keys.
And that cannot be done in parallel, right? Because it's similar to, since every key is associated with a random number.
Yes.
So you could think of that operation as your random number.
So there's kind of conceptually and how I know they actually do it. So conceptually, it wouldn't be a big problem because you could binary split. So you could do it in parallel, but it would be an order log operation rather than an order n operation. But actually, I think they do it in order one because I think the way they advance the keys, they can actually jump in certain parts of the key space more easily than others. So actually, I think they can do it in order one, not order log n.
Yeah.
Okay. Okay, so I've got lots of links at the bottom on how random numbers work in JAX, if you're interested in JAX. And if you want to read about the theory of how these splittable generators work, I've got links to the papers that explain exactly how these splittable generators work. And like I said, they are what's used by default in both JAX and DEX. For other languages, it's a choice whether you use them or not, but they do exist for other languages. For example, you can use them on the JVM, etc. Okay. So that is splittable generators. No. Some,
Actually, I have a question for it. Right? I mean, it's not exactly random, but what about the discrepancy sequences?
like Quasi-Monte Carlo type stuff.
Like, is there anything about that?
Sort of splittable Quasi-Monte Carlo. Yeah, I don't know anything about it.
Because several sequences you can judge fairly.
Yeah. So so I skipped over that. I mean, so that was one of the things with early parallel random number generators. They just jumped a long way ahead, and that's how you got an independent thread on a different processor. But again, yeah, that idea didn't really play out for whatever reason. Yeah. Somehow the splittable just works better when you don't know exactly how your parallelism is going to be deployed up front. Do you know what I mean? Yeah.
Just for the discrepancy things, like it feels like if you take an album sequence, for example, you just use a prime number, right? That's like the basis of the sequence. And so you can just pick another one, but like I don't think it would actually work that well. I don't know the details of it.
Yeah, so there are lots of sequences where you can leapfrog ahead, but they have all of the problems that the parallel random number generators have, in that you need to know exactly how many processors you're going to use, exactly how all of your computations map to those processors, and you have to kind of set that all up in advance, and that turns out to be tricky in practice. You know what I mean?
Well, yeah, a lot of the QMC stuff is done in a very sort of number theoretic way, which means you would imagine that if you don't know how many processes you're sending, you just run into strange extra difficulties.
Then it's just like if you just pick the next prime number, right? So if you're doing helping sequences, say okay, like that processor gets like 2, 3, 5.
I mean, it's interesting. To be honest, I was thinking already about the question of the people working with the deterministic sequences. They know what happens when you do the splitting. And it seems newish.
Yeah.
It seems interesting.
Right, so let's
Yes, splitting makes the results harder to depend. So if you got a GPU of 3,000, you've got a GPU of 100.
no, well, that's the beauty of it, actually. So the actual results that you get are deterministic, whether it runs serially on so many cores. That is actually another advantage of it. Whereas if you were using one of these parallel random number generators, clearly your results would depend on exactly how the thing that's parallelized. Whereas actually, no, using these splittable keys, the logic of your program is the same, irrespective of whether it runs in parallel or not. And so the results you will get will be the same, whether it runs in parallel or not. Yeah. And so, for example, if you move from multi-core to GPU, your results will stay exactly the same, which is kind of nice. Okay, so I've got a hands-on for this. So actually what I'm going to do, since most people don't have DEX installed, I'll walk through the DEX one and then I'll let people play with the JAX one. Okay, so here's splittable random numbers in DEX, which hopefully will make some of these ideas a bit more concrete. So you can have a key and you can split it. But you obviously just look at it, right? So it's better to actually play with it in the record, but whatever. So there we've got K0 is our initial key, okay, which isn't the seed, right? So that shows you that key is not equal to a seed. That's good.
That is a state, no?
A key is basically the name they use for states, exactly. It's the internal state. So we see our key 0 there, our key 1, our key 2, they're all different, okay? And we can use those keys to generate a random number. And obviously, if we keep using the same key, right, we keep getting the same random number, right, which is probably not what you want, okay? So you probably want to use a different key. But clearly, if you use key K1, K2, we get different random numbers, okay? So that's fine. But getting back to this splitting thing, you don't have to just split into two, right? So all of these key generators have a way of splitting many times. Exactly how they're implemented is a little bit subtle, but actually it's quite easy to read in the DEX source. So in the DEX prelude, they've got just the source code for the key generation, and it's relatively easy to read. So that's probably, if you want to actually read real source code, the DEX source code is probably as easy as any. But for example, you just say split, right? And again, there's type inference happening here. So because the thing on the left has 3 elements, DEX knows that the thing on the right must have 3 elements, so it knows that the type must be to split 3 times. Yeah, so a little bit subtle there, but anyway, we can get 3 new keys. That's all fine. We can just say, okay, I want to split. But again, DEX determines how many times to split on the basis of the types. So if you tell it, I want 10 things on the right, it will give you 10 things. Okay. So it does that. You can also use the for notation. Like I said, DEX relies very heavily on this for notation. So if you say, okay, well, if my for loop is going to range over an index of length 8, then clearly I'm going to get 8. And again, this is using this IXT function. And so this is this issue that you can advance the key or split the key in order 1 time with a jump ahead somehow. Don't know exactly the details of how it works, but you can. Okay, so that gives you 8 new keys with basically an order 1 operation. So very often in code, what you'll do is you'll get a whole load of keys, and then you'll map it to get a whole load of random numbers in some way. Yeah, so this is kind of very common pattern in code. We'll just create a load of keys and then map it to get a random number, and then maybe do something with the random numbers, like sum them. If you really just want to advance the key, like old school, and not actually split it, well, you just split it once, okay? You just get 1 key back, that's fine. That gives you a new key. Yeah. And yeah, you can do that in 2 different ways. And so then, you know, somehow you've got to do something with these random numbers, okay? And so actually, I wrote the stats library for DEX, which gives you like the usual sort of probability distributions, and you do the usual things with them. But the point is, if you want to draw, you have to pass in a random number, okay? So the way the stats library works is you create a random distribution like an exponential 2. So that's just an object representing an exponential random variable with rate 2. But it's not a draw from it. It's just an object representing that distribution. If you then want to draw from it, you call the draw function with the distribution, the key, and that will then give you the draw. So similarly, you create a class of random variable in 10. If you want to draw from it, you need to give it a key, and it will give you the draw. And so the kind of pattern you see regularly in code is you have a bunch of keys, you have a random variable, and you map the draw function over it to get a bunch of draws. No. So you split the keys and then you use the keys to do your computation. That often leads to quite efficient code. Okay, so you're effectively just mapping over the keys to get your random draws. Okay, and then we get back to the whole currying thing. So if you're defining your own random function, right, so you did one particular favorite distribution, okay, you want to write the function to draw from it directly, okay, you do that. So, you know, say we were creating a function called rex, kind of R-like. Well, what would it need? Well, you'd need to know the rate, but you'd also need a key in order to actually draw. So that's kind of one way you could write this function. You could write it so that you can just provide the rate, okay, and get back an object representing that random variable. Because that way you can then apply multiple keys and get multiple draws from it, which you might want to do, okay. So you probably want to separately curry off the float from the key. But basically, you always want the key to be the last argument, because that's the thing you want to supply last, typically, right? So you want to create the random variable object, but then the last thing you want to do is give it a key, because that then gives you an option to map the last version of this over a collection of keys. Yeah, so this is why the standard pattern with these kind of generators is to make the key the last argument. I don't think it's uniformly observed in JAX actually, but that's another matter. But it's much neater to make the key the last argument, okay? Because then you can just create a random variable and map it over a set of keys in order to get a random results. So the order in which you curry your arguments does actually matter. You can always recurry it later if you've messed up, but it does make it much cleaner if you get the order of your arguments right in the first place. Okay, now most of you I know have JAX installed, so probably the thing to do now is just to have a play with these splittable random numbers in JAX, and I've got some code here that you can just copy and paste in and start playing with these splittable generators in JAX in the Python REPL. And yeah, you just have 5 minutes or so to do that before I wrap up.
The order basically corresponds to the fact that with a random function, rather than give an input, it's a random output, or we could generate an entire random function. Basically that distinction, right?
It is, and it's nice from multiple levels, because one of the things I like about it is that if I'm programming in a pure functional language, right, I want the type my function to tell me about it, and knowing whether it's random or not is like an absolute crucial fact about my function. And so if I've partially applied some arguments, right, it's still a deterministic function, yeah. And so the fact that the key is there tells me actually this is intended to be a random function, yeah. It's a deterministic function, but it's random in the sense that if I give it some key, it'll be some random output. So having the key there is yeah, it's kind of really nice for kind of making it clear what your code does. But yeah, I think basically you're right. You're distinguishing between the random variable and the draws. And essentially by putting the key last, you're leaving that distinction right till the very end when you're actually using draws.
So when we check P0, we get a one-dimensional, no, it's a two-dimensional.
Oh, that's good.
Okay, so yeah, I think, is this in Python?
Yeah.
Right, yeah, so the really important point, right, that in JAX, the key is a pair of long integers. Yeah. So one key is a pair of long integers. So in Dex, right, it was just this big long thing. But in Jax, it's a pair of long integers. So it looks like a vector with two elements, but that's just a key, right? That is an internal state. It's a pair of long integers.
Okay. Oh, yeah, it doesn't change the meter, it change the. So it doesn't even have its meter banks. But, and each one of the guys, need price. It's a conducting of space. It's not make it easy one and a few, right? So if you have one, then you just it's really. Yeah. And you've thrown away, and it's thrown away your then.
Well, it depends. Okay. So in a pure functional language, you wouldn't throw away the old one because it's all immutable, but actually it's quite common to see in Python Jax code, people do overwrite a old key with a split key, which always makes you feel a bit nervous, but it does seem to work. I don't know how routine people use partial application in Python programming, but it turns out you can. You want to do some of these cool functional programming tricks.
So we do it, at 252 splitting between and 352 splitting between. Because this is very different. And then you, the simple thing would be somehow you take the first half of the second half. So the sequence will make sense. Exactly, yeah.
So
It's like, it's not exactly the same. They have the,
Funny that,
Yeah, that'd be equivalent. That's effectively.
Isn't this?
Yes.
Okay.
So that's very natural.
Element.
Is there an advantage? Because I've seen often using the partial.
No, it's exactly equivalent as far as I.
Okay.
It's easy.
Okay, I don't know if that's so.
No, come again.
Yeah, I think
We got that.
The thing is they have, and one of the reasons I never read the QFC is they have many different people. Some of which are very similar to one another.
Okay, so I definitely don't want to overrun the lunch block, so it's probably time to think about wrapping up now. So obviously this has been like insanely fast and intense, and probably a bit of it's gone over your head if you're not used to thinking about all of this stuff. But what I hope you've got out of this is that functional programming is kind of interesting generally, and is actually very relevant to this whole issue of doing things in parallel and concurrently, and then a lot of the interesting recent developments in parallel and concurrent computing for scalable statistical computing, and especially machine learning, are actually very much inspired by functional programming ideas. Things like JAX are effectively a function language beside Python. DEX is really a pure function language for this sort of thing, and the reason is because the functional programming kind of solves these parallelism and concurrency problems to a large extent. Okay, so hopefully that's what you've got out of this. But then the question is, what now, right? Where do you go next? Learning functional programming is a bit of a learning curve, and so you need a strategy if you're going to kind of investigate this further. Personally, my own view is that it's actually nicer to learn a little bit of functional programming in a proper functional programming language like Scala or Haskell, and then go to a language like JAX or DEX, because then things will make sense. Whereas if you go straight into JAX without knowing anything about functional programming, it probably all seems a bit mysterious. I mean, I know lots of people do it and they manage it, so maybe it's fine, maybe it's just me. But personally, I think that there's something to be gained from that. But whatever you do, right, the thing to do is just to kind of pick one. I've gone through 4 languages here, but just pick one. It's a big one, could be something different, and dive into that in a bit more detail, because it really helps, you know, solidify your knowledge when you kind of dive into one thing in more detail and really unpick how you actually do things. So think about diving into something and learning a bit more about it, and don't be in too much of a rush, right? You know, it really is a lifelong journey. It'll probably take you years to like become like a really expert functional programmer, but that's fine. What's the rush, right? You know, life's long. So if you want some kind of immediate more examples of this kind of thing, and in particular, obviously we just dived into randomness at the very end, but I've got a whole repo on MCMC codes for this logistic regression example. So it's a logistic regression example, but with the Metropolis Hastings samplers, Longevin samplers, Marma, HMC, all coded up from scratch in all of these languages and frameworks, and actually more. Okay, so if you want examples of doing MCMC codes, parallel functional programming languages, right, that repo has all of those examples in it. If you want to learn a bit more about Scala, which, you know, again, I recommend as a kind of good introduction to functional programming, I've got a bunch of resources here. Yeah, so this book, right, and it's a real paper book that you actually have to pay money for, which is a bit annoying. But this book, Functional Programming in Scala, I think is probably sort of the best, most accessible introduction to programming in a functional way for any language, right? So not just for Scala. I think this is like a really fantastic introduction to functional programming. And I've kind of hinted at why kind of pure functional programming kind of butts up to category theory in various ways, and how you can use abstractions from category theory in order to make your code more efficient. Well, there are libraries to support that in Scala, like CATS gives you, you know, your functors, your monads, your applicative functors, etc. But optics is another thing that crops up that I haven't talked a lot about. So Monacle is a nice lens library that gives you lenses and prisms for digging data structures, and as I was saying, great. That connects nicely like if samplers being able to dig into a state, update the state, move on. So Lens has turned out to be useful for that. Breeze is a bit like NumPy for Scala. Smile is a bit like scikit-learn for Scala. Apache Spark is what you'll definitely want if you're doing big data processing on a cluster. There are a bunch of tensor library bindings for Scala. None of them are satisfactory. None of them are really well maintained. I think the best one, actually, because it's the most actively maintained, is Storch. Okay, so that's like Torch for Scala as opposed to PyTorch. But it's based on Torch, which I don't really like, but you know, that's just how it is, right? So if you do want a tensor library in Scala, Storch is currently your best bet. Actually, as Chris mentioned yesterday, GIS people love doing big data processing with massive rasters in the cloud. So GeoTrellis is the way to do that in Scala, and that runs on top of Spark. I've got a course on statistical computing and data science in Scala. However, it's based on Scala 2 and is a little bit out of date. So yeah, your mileage may vary. And I've got a couple of Scala libraries. Haskell, as I said, is like the language of functional programmers. And so knowing a bit of Haskell syntax is very useful. There's a very nice free online book, Learn Your Haskell for Great Good, that you know, some people like, some people hate. It's a very idiosyncratic style that it's written in, but it's quite friendly and informal, and so lots of people like that as a good introduction. So that would be the alternative to functional programming in Scala, I guess. Learn Your Haskell for Great Good. Type Classopedia tells you about all of these category theory type classes and where they come from and why you would want to use them. There is Data Haskell project for data in Haskell, and there are various sort of auto-defined, as there kind of are in Haskell, in Scala as well, but none of them are absolutely general, right? So none of these libraries are like DEX, where the whole language is differential. But if you want to investigate auto-diff in Haskell, there are various libraries to support that. JAX, I've mentioned. The documentation for JAX isn't too bad if you know about functional programming already, and if you don't, then it's a little bit mysterious. It's interesting to look at the DeepMind JAX ecosystem, see how they're using it. DEX is a bunch of stuff online if you want to learn more about that, but there isn't a huge amount of documentation for it, and what documentation there is goes out of date quite quickly. If you're interested in this connection between category theory and functional programming, there's this very interesting chap, Bartosz Milewski, who was originally a C++ developer for Microsoft, but kind of saw the light and became a kind of Haskell and category theory wizard, actually, who was originally a theoretical physicist. So he's a theoretical physicist turned C++ developer, now turned kind of Haskell and category theory wizard. He's a really interesting guy. He has a whole series of blog posts about category theory and functional programming. The blog posts were turned into a book. He also has a bunch of series of YouTube lectures accompanying the blog posts that I found actually very helpful, a bit more accessible than the blog posts. So if you don't understand the blog post, maybe watch the videos. But he's now actually written a proper book. So this book, Category Theory for Programmers, was basically just a concatenation of blog posts, but he's actually sat down and written a proper book called The Tao of FP. And so that is probably the go-to resource on why category theory and functional programming are closely related and why it's important. If you're interested in functional programming and category theory for machine learning, there's a nice repo of resources on basically a list of papers that link category theory and machine learning. If you're interested in how DEX and JAX do automatic differentiation in a functional way, that is the paper. You only linearize once. If you're interested in learning more about pure functional data structures, so we talked about these data structures that you can update in a pure functional way without copying everything, right? Well, there are a bunch of these things, not just the vector type that I told you about, and there's a whole book on them. And in fact, you can find the PDF online, though. Whether that's legal or not, I don't know. If you're not taken by any of these languages I've talked about, there are other interesting languages. So OCaml is another kind of interesting language that's quite functional, not quite as functional as Scala or Haskell, but it's kind of a nice language. Flix is a sort of new take. It's sort of a Scala-like language, but a bit different. That's kind of interesting. Futhark is a pure functional language specifically for programming GPU. So if you really want to just do GPU programming, Futhark is kind of interesting. And as I mentioned to a couple of people, there's this sort of halfway house between it's not really a functional language, but it's actually not as barbaric as C++. Rust is a possible alternative. It's quite a nice language. It's not properly functional, but it's been very much inspired by functional ideas. It does have mutable collections in it. So you can choose between using mutable or immutable collections. So you can actually write quite good, solid functional code with Rust if you try hard enough. So that's another possibility for people to look at. And yeah, so hopefully there's enough there to allow you to kind of continue this journey if you want to. And yeah, that's it from me.
Much, Darren.